Here is an introduction to exoplanets to accompany Chapter 21 of the textbook Astronomy from Open Stax. When we talk about exoplanets, we just mean, it's an extrasolar planet. Right? It's a planet that's orbiting a star that is not our sun. That's straightforward enough. But the definition has to be different than the definition that we use for planets in our solar system. Because, for the solar system, we have these three criterion. It has to be orbiting the sun in the solar system. It has to be orbiting a star for an exoplanet. In the solar system, it has to be spherical, but here we don't know whether or not these are spherical. In the solar system, it has to be clearing its own orbital path, but we don't know that. We can't, for reasons we'll talk about, we can't really tell if that's true or not. But practically speaking, as we'll see, the objects we can see are large enough, these things should be true. Okay, but we can't use that criterion, we need to have something different. So instead, the ways you can define it are just concerned with the mass of the object and its formation. So an exoplanet, it has to not be so massive that there's nuclear fusion that can happen in the core. Now, when we talked about stars and stellar evolution, we talked about hydrogen burning turning on. It turns out you can burn deuterium, which is an isotope of hydrogen. You can burn deuterium first, and that happens when you're around 13 Jupiter masses. So an exoplanet has to be less than this, otherwise you'd consider it something called a brown dwarf, which is basically like a star that can only burn deuterium at the core. So it has to be less than that mass limit. And really, if you want to be a stickler about it, it's not just the mass, it's also the formation. So we talked about in the introduction to planet formation that planets form by accretion, so they build slowly, whereas introduction to star formation, stars form by a direct collapse of a cloud. So if you want to be a planet, you should really be building by accretion and not direct collapse. In terms of the census that we have of exoplanets, as of right now, there are around 4,600 confirmed exoplanets. There's almost as many that we suspect are exoplanets, and by suspected it means that there are signals that indicate this is an exoplanet, but it doesn't meet the strength of evidence that one would want, so that it needs some kind of follow-up confirmation. And most of these are located, within a few thousand light years. You can see many are very close, within a few hundred light years. And the reason for this distribution is just it gets harder to detect planets the further away they are. So there's not anything special about this distribution. This really says more about our effectiveness to find planets than it does about where they're located. In fact, from looking at our local stellar neighborhood, it looks like most stars have planets. So it would be unusual for a star not to have at least one planet. So let's go through the different ways we can detect these exoplanets. So direct imaging is one method. So in a perfect world, we would just look at a stellar system, we'd just look at the light from the planets, and we'd be good to go. The problem is that stars are really bright and planets aren't. So stars, right, are nuclear reactors. They're shining brightly, whereas planets, they only reflect the light from the host star. So by their very nature, they're extremely dim. Nonetheless, in some cases, what you can do is you can block out the host star's light, and for relatively close systems, you can block out that star's light, and then you can see separated from that objects glowing in the infrared, and they're basically heated by the star, and you see their infrared radiation, and you can even follow these planets as they go around their host star. So this is only going to work for planets that are at the right orientation relative to us, and generally ones that are pretty close. Sometimes, in cases we can't see the planet directly, we can see the impact on the protoplanetary disk. So this is a really neat simulation here on the left, and then on the right is an actual observation. You see this protoplanetary disk has a spiral-like feature and regions of kind of enhanced density, and you can simulate that this kind of thing can happen due to gravitational perturbations from a planet. Now, of course, as we talked about in Introduction to Planet Formation, these protoplanetary disks are only around for a few million years, so this is really only useful for young planetary systems. And so for most stars, this is not an option. You cannot do direct imaging. It's a minority of systems that we can image. Another way we can detect exoplanets then, and in fact the rest of the ways, have to do with basically the impact of the exoplanet on the star or stars that are nearby. So in this case, what we can do is, I shouldn't say star or stars nearby, it's just the star that the planet's at, right, is the right way to say it. So one way you can detect these planets is through microlensing. So we talked about gravitational lensing in the galaxies and dark matter lecture, and this is the same thing. Now what you have in this case is you have some distant star. We're looking at its light. Its light can be gravitationally lensed by a nearby star. And when the exoplanet basically is located at a certain position with respect to its host star, that will change how the light from the background star is lensed. So the lensing makes this star brighter, and then the planet itself changes that brightness. It enhances it a bit, right? Because you not only now have lensing from the star, you have a little bit of extra mass, and that can cause this kind of blip. And so the way this works, right, is you have your star is passing in front of the background star, and as it gets in front of it, the lensing is enhanced, you get more light, and then there's a small change here, and that is due to your exoplanet. So that's one way to detect exoplanets. It's it requires very special conditions. You have to have this sort of setup going on here. And so again, this is not how most systems are found, but a good number are found this way. An extremely common method for planet detection is the radial velocity technique. And you'll remember this from the introduction to the HR diagram for how we obtained stellar masses. So what's happening here is you have a star and there's a planet going around it, and while you may think of the planet just going around the star, in reality the two are going around some center of mass. Now in this cartoon here, this is a very exaggerated cartoon, but this is essentially what's happening is the host star is wobbling. So these two things are really orbiting each other, so you can think of this host star is moving in an orbit as well, towards us and away from us. And the cartoon is exaggerated, but this is what is happening. And so light in one part of the orbit, or wobble, if you want to call it that, is going to be blue shifted, and the other it's going to be red shifted. And we can image this, the shifting of these spectral lines over time, and get a radial velocity versus time diagram. So from this, we can determine the period of the orbit. Okay, and then we have Kepler's third law that relates that period to the orbital separation of the star and the planet, combined with the sum of their masses. Now, what's different here from the stellar mass case is that the mass of the star is basically the mass of the whole system, right? So planets are much, much less massive than the star, and so the sum is essentially just the mass of the star, okay? So then the orbital separation cubed is proportional to basically just the mass of the star times the period squared. We get the period from this radial velocity phase diagram here. Now, the mass of the star we can get from the location on the Hertzsprung-Russell diagram, as we've talked about in the past. So from this, we can solve for that orbital separation. Okay, so we can directly figure out the orbital separation of the planet from the star, which is pretty cool. But we can go further. We can use Newton's law of gravity to figure out what the velocity of the planet is. And we don't need to worry about how you solve this equation. It's relatively straightforward, and if you take Physics 2001, you can do it. The velocity of the planet is equal to the square root of Newton's big G, this is constant, times the mass of the star divided by the orbital separation. So again, we've gotten the orbital separation from Kepler's third law here, and the mass of the star from the position on the HR diagram. So we know the velocity of the planet, which is pretty cool. And we can take that further. There's a thing called momentum conservation. Again, you could learn about this in Intro Physics, the Physics 2001, if you wanted. And this tells us that the momentum is conserved, so the mass of the planet times the velocity of the planet is equal to the mass of the star times the velocity of the star. Now, we've already measured the velocity of the star from this radial velocity diagram, right? We can determine what its velocity is. We get the velocity of the planet, as we talked about here, and the mass of the star is from the HR diagram, and so you can use all of this to solve for the mass of the planet. So this is kind of amazing. From this radial velocity technique, you get the mass of the planet, and you can get its distance from its host star, which is pretty neat. Now, one complication here is this only gives you a lower limit on the mass because you only measure the motion in a line of sight, right? You see how much the star moves towards you and away from you. If the planetary system is tilted, then this isn't going to be perfect, right? You're only going to measure a fraction of its true radial velocity, and so this gives you just a limit on the mass. Again, from the from the Intro to the HR Diagram lecture, when we talked about getting stellar masses and radii, there's the transit technique, and this can be used for exoplanet detection. So it's the same concept where your system just so happens to be that the planet is passing between the star and us. And we look at the light from the planet, or from the star rather, and that light dims when the planet passes in front of the host star. Okay? And as with the radial velocity method, we can get the period, right? In this case, we're getting the period just for how often these transits happen. Using that period and the star mass from the HR diagram, we can get the planet-star separation distance. We can get that as well. We can determine the mass in the way we just described for the radial velocity method. But we can also here get the radius for the transit method, right? It's extremely powerful. And the way that we can do that is the fact that the amount of light that is blocked out, it depends on two things. It depends on how big the planet is, and it depends on the distance between the star and the planet. But we've determined the planet-star separation distance using Kepler's laws. So we actually know that. So we can basically get the size of the planet from the transit depth, and in a simple sense, it's basically the area of the planet divided by the area of the star. That is going to be directly related to how much light is blocked out. And so we have this relationship here. These objects are basically circles, and so their area is just pi r squared, pi times the radius squared. If we were to calculate this, the pi's cancel, and so the transit depth gives you the ratio of the square of the radii, but from the location on the HR diagram, we can get the radius of the star. So you can actually use the transit method to determine the radius of the planet as well. So we can get the radius of the planet, the mass of the planet, and the distance between the planet and the host star. And I mean, what more can you want? That's most of what there is, basic properties to know about it, which is pretty cool. And this transit method is extremely powerful, and it's how we've detected most of the exoplanets that we have. The main reason is that it's the most sensitive, and so it's the easiest way to detect a planet, I guess. Now this is going to introduce some bias, because this transit method is obviously going to be biased towards finding larger planets at closer distances to a star, because those things are going to increase your transit depth and increase your signal to noise. So that's a bias. Another bias is, it shouldn't matter too much, but you're only going to find systems where you basically happen to be looking at them edge on, right? So that's because that's the kind that you can find. And you'll see the next most common kind is radial velocity, and then the others are kind of also RANs, basically. One that you can't even see here unless you zoom in is the last one we'll talk about for exoplanet detection, called you can call it the timing method or transit timing. So for transit timing, what we're doing here is we're looking at the variation in the transit time for a larger planet. So in the video, you have some large planet that is orbiting a star, and it's going to orbit it many times, and we can clock the time it takes for the planet to transit the star. And if it's just this single planet and the host star, that transit time is pretty much always the same as the video shows. It's exactly the same. There's nothing to perturb it whatsoever. But if you now add in a smaller planet, one that is not large enough to detect with the transit method, it gravitationally interacts with the larger planet that you can detect via the transit method, the one that's closer into the host star. And this gravitational interaction changes the transit time. So for one orbit, the transit time will be a little bit shorter. For the next one, it might be a little bit longer, and so on. And you can then figure out something about the other planet, and you can detect it in this way. So it's pretty clever. You know, you need to have a very precise measurement of your transit time, and so it's not widely applicable to a ton of systems, and so only a handful of exoplanets have been discovered this way. So now we know, how we've detected exoplanets, how we've determined their properties. So what are the planets, or the properties of these exoplanets? So what we're looking at here is a distribution of exoplanets as a function of the mass. So be careful here, the horizontal axis is a log scale, and we're looking at Jupiter masses. So this bump here, there's a bump around a Jupiter mass or so, and then there's another bump here that's a little bit larger than Earth size planets. So it seems we have a lot of planets that are small and rocky, kind of like a little bit bigger than the Earth, and then a lot of planets that are large and gaseous, and from the statistics we have here, not really very many in between. One reason why this could be is that as we talked about in the introduction to planet formation, you need to have enough mass to be able to capture a hydrogen atmosphere. You need to also be far enough away from your host star that the gas isn't blown away and the gas can condense, but you need enough mass to actually attract that material. And I'll try to explain why you can't do that for the Earth, but you can do that for a Jupiter-sized object. So what's shown here is the escape velocity of a molecule or atom versus the temperature. And you can see for an object like Earth, it's massive enough to capture water vapor, but not massive enough to capture hydrogen and helium. It just doesn't have enough gravitational potential to do it. And there's a lot of hydrogen and helium kicking around in the protosolar disk, or the protoplanetary disk, where planets are forming, because, as we've talked about, the universe is mostly hydrogen and helium. So the idea is once you're a little bit more massive, and you can capture hydrogen and helium, there's a whole bunch to be captured, and so you're going to have a huge gaseous atmosphere, and so you're either going to be tiny and rocky, or you have enough gravity to actually capture this, and you're cool enough to actually capture this hydrogen, and so then you're big and massive, and so that would lead to this kind of gap. You're either one way or the other. But we need to be a little bit careful here, so probably that's true to some extent, but there is also a large selection effect with these detection techniques. So as we've talked about, with the transit method, it helps to have a big old planet that's close to a host star, right? That's going to bias the kinds of things that you detect, and that's the method that we have that detects most of our planets. So that's maybe an issue, and for instance, if you compare these two telescopes, both of them actually use the transit method. One of them is an older telescope, one of them is a newer one, and the inferred mass distribution you get from one telescope or the other would be, I would say completely different. So I don't know that this is the end of the story on the mass distribution for planets. Probably to some extent you can explain it with this massive enough to capture hydrogen and cool enough to capture it, but also it may be this distribution, we don't fully know it yet. When you look at exoplanet radii, you have the same story and the same caveats. So the distribution versus the radii. You have many are a bit larger than Jupiter, and many are a bit larger than the Earth, and there's not a lot in between. And this can be explained with the same things that we just talked about, so I won't repeat it. Now it's even more interesting when we plot the mass versus the radius for the exoplanets that we have both pieces of information. So what's shown here is a plot of the radius in Jupiter radii versus the mass in Jupiter mass. And again, this is log scale, so it's a little bit tricky, but what you have is something that on a log scale is linear up to about a Jupiter mass, and then it levels off. Now really, if you were to plot this on a linear scale, you'd see this is a sideways parabola, and the radius basically goes as the square root of the mass up until you get to be about as big as Jupiter, and then it actually decreases, the radius decreases a little bit with increasing mass. If you actually want to calculate this, this is an upper level thing. You should take Astronomy 4201, but it's something that we can understand in any case. Now we can take our planetary masses and radii, can use the radius to calculate a volume for a sphere, and the average density is just the mass over the volume. And unsurprisingly, when we plot the distribution of the density, these objects are basically in the range of densities that pretty much all liquids and solids have here on Earth, right? So the average density is about the same as water, a gram per centimeter cubed. And you have some planets that are, about 10 times less dense, some that are 10 times more dense, but they're all in the same kind of ballpark here. And then the final piece of information we can talk about for exoplanets are their composition. So the mass and the radius, remarkably enough, actually gives us clues to the composition. So for low mass planets, like rocky planets like the Earth, we can assume that the density is basically just sent by interatomic spacing. So how closely you can pack together material just depends on the separation between atoms. And if you do that, you can plot a mass versus a radius, and you get these arcs that are plotted here. And the interatomic spacing is going to depend on what kind of material you have. So if it's all like nickel, then you're basically following this dashed tan line here. If you have all water, you'd follow this dashed blue line here. And then if you have a mixture, you're going to fall somewhere in between. So for instance, the Earth, which has a lot of rock but also a lot of water, is going to fall along this line. So these general theoretical predictions match the observations, and so a good mass radius constraint actually tells you something about the composition, which is kind of amazing. For the larger planets like Jupiter size and above, it's actually the electron degeneracy pressure that we learned about in the Introduction to Stellar Remnants lecture that sets the density, and that's why these planets' radii more or less don't depend on the mass, or very, very weakly. And again, that kind of matches our theoretical predictions, which is pretty cool. We have other clues to the composition of planets, so we can see how shiny they are in different wavelengths. That's called the albedo. That's gonna tell you something about the composition. Really one of the best ways to get the composition is a spectra. So what you do is you look at the spectrum from a star, or really the stellar system, when there is not a transit and when there is a transit, and you subtract the two, and that gives you basically the spectrum for the planetary atmosphere. The difference is what's caused by the planet, absorption of light in the atmosphere of the planet, and there you can determine, some of the stuff that's in that planetary atmosphere. Doesn't tell you about the core or anything like that, but it does the atmosphere, which is pretty cool. And then, as we learned in the Introduction to Planet Formation, the distance from the star gives you some idea, though that is of course complicated by planetary migration. And so if we plot our different planets here, the size versus the orbital period, we can kind of lump them into these general categories that are somewhat artistically named. We have stuff like the Earth and the rocky planets. If you're super close to the sun, or to the star rather, like even closer than Mercury, you're maybe a lava world because you're so hot that the rock's kind of molten. And then you have stuff that's further out, you know, like for instance, your Neptune, Uranus that are cold and gaseous, and your big objects like you know, Jupiter gas giants that may be further away or may have migrated inwards. And this is kind of the categories you can lump these into. And that is it for this introduction to exoplanets for Astronomy 1000.